Welcome back to The Explainer. Today, we're diving into Chapter 5, and we are going to demystify one of the absolute most profound ideas in modern physics, quantized energy. If you've studied physics, you might have been taught that energy levels are just kind of a given, like this magical postulate handed down by the quantum pioneers. But today, we're going to prove that quantization is actually a strict mathematical inevitability of confinement. It is literally the reason atoms have solid structure and, the reason you don't fall right through the floor. Just think back to the stunning 1993 IBM quantum corral experiment. It is the perfect phenomenon of the day to prove that standing waves of probability density are incredibly real. We're talking about 48 iron atoms arranged in a precise, microscopic ring on a copper surface. And inside that atomic ring, the electron density isn't just some smooth, featureless puddle. It forms a highly distinct, structured, concentric ring pattern. So here is our syllabus for today's session. We are starting with the quantum corral, then comparing it via the guitar string analogy, before mapping out the infinite square well. After that, we'll actually derive quantized energy, and finally, look at what happens when probability sloshes. All right, Section 1, the quantum corral. Let's really break down what happened at IBM's Almaden Research Center back in '93. See, the researchers didn't place those concentric rings of electron density in the center by hand. No, they meticulously arranged the 48 iron atoms into a circle using a scanning tunneling microscope. And the electrons themselves were completely forced into these distinct spatial modes. Why? Simply because they were confined inside that atomic container. The absolutely crucial takeaway here is that quantization wasn't assumed, it was physically forced by the boundary of the atoms. Confinement is the true author of this structure. Moving right along to Section 2, the guitar string analogy. The really crucial point to grasp here is that both of these systems rely on waves vanishing at their boundaries. But what is actually waving is entirely different. Think about a classical guitar string. It's a literal, physical displacement of a medium, right? For a note to actually ring out, the vibrating modes must perfectly vanish at both fixed endpoints. You can fit a half wavelength or a full wavelength, but you can't fit a fractional wave, unless you want to sound like a totally out-of-tune musician. Now, a quantum particle trapped in a container follows the exact same geometric rules. Its surviving modes absolutely must vanish at the container walls. But a quantum wave isn't a physical medium vibrating. It is a wave of probability amplitude in the space of possible positions. Okay, Section 3, the infinite square well. Now, don't let the calculus here intimidate you because it's actually telling a super straightforward story. We're looking at the time-independent Schrödinger equation, specifically inside our imaginary well where the potential energy is zero. Inside this well, the particle's behavior is entirely governed by this exact equation. It's basically just asking us a question: what values of energy, which we represent with E, are actually allowed to exist inside this space? Well, to answer that, we have to establish the rules of the container, what we call the boundary conditions. Imagine our well has utterly impenetrable walls located at position 0 and position L. The potential energy at these walls is literally infinite. And because the particle absolutely cannot exist inside an infinitely high wall, the mathematics completely force the wave function, that's our Greek letter psi, to hit absolute zero at both ends. Any wave modes that contradict themselves and try to exist at the boundary, they just instantly collapse. When you map this out visually, the abstract math turns into a really beautiful reality. You'll notice how the standing sine waves rest on distinct energy levels inside the well, and look at the spacing between those horizontal energy lines. They aren't evenly spaced like rungs on a normal ladder. Actually, they grow exponentially as n squared, so the gap between the first and second state is much smaller than the gap between the fourth and fifth state. The energy levels just widen their gaps as you climb higher and higher up the ladder, purely because of how those sine waves have to geometrically fit between the walls. Which brings us perfectly to Section 4, deriving quantized energy. Let's walk through this differential equation step by step using a simple process of elimination. First off, we rule out negative or zero energy. Those just lead to a flat line where no particle exists at all. So, moving to step 2, we solve for positive energy, which gives us a non-trivial solution mixing sine and cosine waves. Okay, step 3, we apply our first wall at position 0. Now, because the cosine of 0 is 1, but our wave absolutely must be 0 at the wall, the cosine term is eliminated entirely. It simply can't exist here. That leaves us with just a sine wave. Finally, in step 4, we apply our second wall at position L. That remaining sine wave absolutely must equal 0 at that far wall. And that specific condition, that is our fundamental aha moment. It's the exact point where the continuous world collapses into a discrete reality. Because a sine wave only crosses zero at integer multiples of pi, the wave number k multiplied by the length of our well L must equal n times pi. And n is just an integer, like 1, 2, 3, and so on. I really want you to absorb this quote from Chapter 5. Notice what the math is screaming at us here. Quantization was not postulated by Schrödinger as some arbitrary, made-up rule. Not at all. It was strictly derived from the undeniable geometric fact that a sine wave can only hit zero at integer multiples of pi. Because the wave has to fit exactly between the walls, only certain specific wavelengths, and therefore only certain specific energies, can survive. I'll say it again. Confinement creates quantization. Finally, Section 5, when probability sloshes. To understand this, we first have to define a stationary state. If a particle sits completely in just one single energy level, let's say the very bottom rung of our ladder, it is perfectly stationary. If you were to track its probability density, it remains totally frozen in place over time. The only thing changing is a complex mathematical phase that rotates completely invisibly in the background. The observable probability doesn't move a single inch. But things get incredibly dynamic when we look at the sloshing state. If we create a superposition by mixing two different energy levels together, say rung 1 and rung 2, something absolutely fascinating happens. Because they have different energies, their complex phases rotate out of sync at different rates. This mismatch creates an interference term that beats at a specific frequency. And the physical result of that? The probability density is no longer frozen. It constantly sloshes back and forth across the well, shifting continuously through space over time. So to get any motion at all in quantum mechanics, you literally require this superposition. Now that we've mathematically derived exactly how completely impenetrable walls build the discrete quantum ladder, I want to leave you with a final provocative thought. What kind of bizarre phenomena occur when those infinite walls are lowered? I mean, if the walls have a finite height, the boundary conditions change and the wave function can actually leak through into classically forbidden regions. How in the world does a particle pass through a wall it mathematically shouldn't have the energy to cross? Well, that is the incredible reality of quantum tunneling, which we'll explore next time. Thanks so much for joining me on this explainer, and keep questioning the quantum world.